Welcome to CSIT212 Introduction to Computer Systems Remote Lessons. Scheduling criteria and algorithms. So the criteria are as follows. CPU utilization, keep the CPU as busy as possible. Throughput, number of processes that complete their execution per time unit. Turnaround time, amount of time to execute a particular process. Waiting time, amount of time a process has been waiting in the ready queue. And response time, amount of time it takes from when a request has been submitted until the first response is produced, not output. Scheduling algorithms. So the CPU scheduler, also known as the short-term scheduler, must select appropriate processes to be executed. As mentioned before, processes are selected from a ready queue. The queue can be in any representation, that is priority, stack, tree, unordered. The kind of scheduler being used will influence the data structures used. Conceptually though, just think of it as a series of processes, control blocks or PCBs. There are various scheduling algorithms and we will be talking about a few of them here. First time, first come, first serve, or FCFS. So imagine you have these processes, P1, P2, P3, with these respective burst times. So if you had to actually draw them in a Gantt chart for the processes as they arrive in order, this is what they would look like with these times. So accordingly, waiting time for P1 is as follows, with the average waiting time as calculated. So here's a short video to just quickly show you how the first come first serve works. So you have the processes P1, which is supposed to take 24 burst time, P2, which will take 3, P3 will take 3. So when I make a Gantt chart for this, okay, so I'm going to start of course with P1 because P1 is supposed to be coming first. So it starts obviously at 0, but then it goes all the way to 24. Okay, then you bring in P2, which takes 3 burst times. So 24 plus 3, you get a 27. And then P3, which basically starts at 27 and finishes at 30. So when you have this, the waiting time, then for P1 becomes 0. P2 becomes 24 and P3 becomes 27. Problem here then becomes when you look at the average time, you add up all of these, 0 plus 24 plus 27, divide the whole thing by 3, you get a 17. Looking at the same example, so suppose that the processes arrive in this order, P2, P3, and P1. So then your Gantt chart is going to look slightly different as this. So then your waiting time becomes so, and the average waiting time as calculated becomes 3. The next slide gives you this demonstration. So for the same example, but if we this time said the order was P2, then P3 and P1, given we are looking at first come first serve, so the Gantt chart would then look something like this. We know at the end it's still going to be 30. The starting point is of course 0, but this time the first one to go is P2, which we know is only 3 burst times, right? So then you have 3 here. Okay, then we have P3 which we know again is 3. So then it is 6. So automatically you see now P2 is starting at 0 and P3 starts at 3. Okay, and then you've got of course P1, which is 24. Okay, and then that kind of covers this. Okay, so this way, then the waiting time for P2 is 0. P1 is 6 and P3 is only 3. Okay, so here you've got it coming in this way. All right. So when I calculate the average waiting time, then it becomes 6 plus 0 plus 3 divided by 3, which is only 3. So in this case, it does look like the average waiting time is going to be much better than the previous case, because in this case, the first come, first serve was P2, P3, and P1, and not P1, P2, and P3. The next algorithm is shortest job first, or SJF. So associate with each process the length of its next CPU burst. Use these lengths to schedule the process with the shortest time. SJF is optimal. It gives minimum average waiting time for a given set of processes. The difficulty is knowing the length of the next CPU request, though. Here is an example. So you have process P1, P2, P3, P4 with the corresponding burst times 6, 8, 7, and 3. So when we look at the scheduling chart, P4 will start first, naturally, because that's the shortest, with 3. Then P1 with 6. Then P3 with 7. Then P2 with 8. So the average waiting time here then becomes 3 plus 16 plus 9 plus 0, which is 4, divided by 4, which is 7. The next one is priority scheduling. Priority number integer is associated with each process. The CPU is allocated to the process with the highest priority. Smallest integer equals to highest priority, which can either be, you can either have a preemptive or a non-preemptive. Now, SJF is a priority scheduling where priority is the predicted next CPU burst time. Problem equals to starvation, which is low priority processes may never execute. And the solution is aging. As time progresses, increase the priority of the process. Let's look at how this works. So if you've got this table, now the first two columns is what you have been seeing so far, the processes and the burst times. Now we have an additional column called priority, right? So as you can see, P1 takes 10, P2 takes 1, P3 takes 2, P4 takes 1, P5 takes 5. But here is how we will actually follow this, right? P2 has the highest priority, then P5, then P1, then P3, and then P4. So then this is how you would actually end up drawing the Gantt chart for the priority scheduling. In this case, the average waiting time then becomes 8.2 milliseconds. Finally, round robin, or RR. Each process gets a small unit of CPU time or time quantum. Usually it's between 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. If there are n processes in the ready queue and the time quantum is q, then each process gets 1 over n of the CPU time in chunks of at most q time units at once. No process waits more than n minus 1 times q time units. The performance then becomes q large, FIFO, and q small, which is q must be large with respect to context switch, otherwise overhead is too high. Now context switch is switching from one process to the another. We will be looking at it more closely in the following sections. Here's an example of a round robin with a time quantum of 4. So you've got the processes P1, P2, and P3, as you can see here. Now on the second column, you've got the burst time, 24, 3, and 3 corresponding. Now the Gantt chart here is very important to notice. You will notice that for P1, although it says 24, we can only do 4 because our quantum time was 4. Q was 4. Then we move to the next one, which is P2. We are going to give it a slice of 4, but it only needs 3. So we take 3 and then we move on to P3. Again, we want to give it a times quantum of 4, but it only takes 3. So we give it 3 and then we move back to P1. Now that doesn't mean of the 20 now remaining, we do everything together. Even that 24 then gets sliced into 4s. So again, you have 14, then 18, then 28, 26, and then 30. Typically higher average turnaround than SGF, but better response. Q should always be large compared to context switch time, and Q usually is between, like I said, between 10 milliseconds to 100 milliseconds, and the context switch should be usually less than 10 seconds. So time quantum and context switch time. Here's how this looks. So if you've got the process time, which is 10, and I say the quantum is 12, context switch is 0, this is how this will look. But the moment I increase the context switch to 1, my quantum then becomes 6. And then I will increase the context switch to 9, and then my quantum becomes 1. So this illustrates how a smaller quantum increases context switches. Segment activity. Scheduling, practicing algorithms. So consider the following set of processors with the length of CPU burst time given in milliseconds. The processors in this table are assumed to have arrived in the order P1, P2, P3, P4, P5, all at time 0. Attempt these 4 questions and upload your answers in the Moodle submission folder. Have you completed the task? If you have completed the task, please continue. End of segment.